Okay, so let's begin. Assalamu alaikum and good afternoon to everyone. And thank you very much for joining this second workshop on quantum computing. I hope most of you were also present in the first workshop by Aisha on the basics of quantum computing, where you learn to work with the 1 or 2 qubits, and you also learned how to use Hadamard and control X gates to prepare entangled states, and then to transmit either classical or quantum information from one place to another place using qubits. So, but this present session will be focused on a slightly advanced topic than the one covered in the last workshop. And in this one, we will actually use quantum computer to do something something that we are used to do on a traditional computer. For example, on a traditional computer that we have, we are able to write different programs to solve different problems. And so this session will essentially try to introduce you to quantum computing in general. And for that purpose, I will take a concrete example of a slightly advanced algorithm than the simple algorithms that you studied in the last workshop. And hopefully, by that algorithm, you will be able to get an idea how quantum computers work, and where do they drive their power, and why they are so much hyped. That we'll see that we will study an algorithm that solves a problem using fewer number of operations than what can be done on a classical computer. And the example that I have chosen for that is a quantum search algorithm. The reason is this, that that was also the algorithm that when I started learning quantum computing a year ago, that was the one that struck me for the first time, because it's a bit easy and also tells you how quantum computers are different from classical computer, and sort of can train you in understanding and implementing other algorithms as well. So the format of this workshop will be like this, that I will share the screen of a notebook that I will be working on that algorithm and explaining you different algorithms. The class online? Yes. So, sorry, there was somebody at the door. Then I will discuss the basics again very quickly, so that anybody who's joining now can come online. And then I will go on and explain the search problem, and we will see how to solve it on a classical computer. And then we will discuss the quantum algorithm for that, and at the end we will compare both the techniques, and we'll see that quantum computer can do it faster than a classical computer. And at the end, I hope there would be enough time, and I'll show you a program in Python that I have written, and we'll see the simulated result, but the same thing can be transported to IBM quantum computers, and for that matter to any other computer, and it will work just as fine. So by the end of this session, hopefully you will have some idea of how quantum computer algorithms are analyzed, and how they are implemented, and how they are different from the classical algorithms. So let me start sharing my screen. Okay. And for questions, please keep posting your questions in the chat. Unfortunately, since I will be focused on this screen, I will not be monitoring the chat. But at the end of this session, I will go through the questions and answer your questions. I would have actually loved it to be a little bit interactive, that where you have any question, you can pop in the middle, and then I would like to answer. But it's set up in a way that you cannot unmute yourself. And actually, what we can do that instead of me going through the questions at the end, what I can do that every like 10 to 15 minutes, I will stop and go through the questions in the chat and respond to them, and then we'll get back and so on. So perhaps this way we can make it a little bit more interactive than just answering all the questions at the end. Okay, so I hope that you can see my screen. If no, just write no in the chat box. All right, so let me just give you an overview of this workshop. So I will cover basics of single and multi qubit gates. We'll discuss the quantum computing model, which is the circuit model. And then I will discuss the quantum search algorithm that hopefully, along the way, I would be explaining the concepts in a way that you should be able to get a general idea how does quantum algorithms work, not just the quantum search algorithm. This is also called Grover's algorithm because he was the one who first discovered it. So this Grover's algorithm will serve as an example for us to understand quantum computing. All right, so let me start from the basics, and let's start from qubits, which you're hopefully already familiar with from the previous workshop. So a qubit is just a two-level system, as Aisha was telling you about. And let's say we designate those two levels with 0 and 1. So it's a two-level system, and a classical bit is also a two-level system, but there's a one major difference. Classically, you can either be in this 0 state or 1 state. That's it. But quantum mechanically, we can access an infinite number of states, which are essentially superpositions of these two levels, with the restriction that this is a normalized state to make sense of the measurements. So this is our qubit, which is essentially a two-level quantum system. And since these alpha and beta can be complex numbers, so in general, we can specify this qubit with 4 parameters, like 2 for alpha, real and imaginary part, and 2 for beta, real and imaginary part. But because of this constraint, we essentially have 3 independent parameters. And if we ignore the global a parameter which represents the global phase, we're essentially left with 2 parameters. So that's why we can represent this qubit as a state on the surface of a unit sphere, because this is the surface is specified by 2 parameters, theta and phi. So neglecting the global phase, we can represent the state of the qubit as a point on this sphere, which we call Bloch sphere. Okay. All right. So let's now discuss the gates. So the gates are essentially operations, unitary operations on a single or multi-qubits. So a single qubit gate is essentially a unitary operation on a single qubit. So we can define many operations, but one of the few that we will need in this part of this workshop Let me just quickly review them. The X gate, which is one of the common gates. Some people represent it with sigma X, but I'll be using just X. So this is a simple gate, which when X on 0 gives us 1. And when this X gates X on 1, it gives us 0. So if I give it a symbol, I can do it like this. So this is input state, and this is the output state. And I can represent this gate in several ways. And two of these ways which are more common is, one is the matrix representation, because the state 0, I can, let's say, represent it with a column vector 1 0, and this one state with 0 1, which means that my X can be represented with a matrix like this, because of this special placement of the zeros and ones. When this X acts on 1 0, it gives us 0 1, and when this X acts on 0 1, it gives us 1 0. You can actually check it very easily. Another way of representing this X is actually using Dirac notation, that I can write this X as 1 0 plus 0 1. So because we can easily see that when this X acts on 0, so this means this 0 is operating on the from the right. So this 0 comes here, and by using the orthogonality of states, we can see this when this 0 is inner product with 0, I get 1. And when this 1 inner product with 0, I get 0. So ultimately, I get 1. Similarly, when this X operates on 1, you can check with this notation, you will get 0. So I can use this operator form as well to represent these gates, because these gates are nothing but unitary operations on these qubits. Okay, so this is one example. Let's talk about another example. Another example is Z gate, or a phase gate. So this is a gate which can be represented in matrix form using this thing. So this multiplies state. This gives state 0 as it is. But if this Z gate operates on state 1, it multiplies it with minus sign. So it essentially gives it a phase of 180 degree, because exponential iota 180 degrees minus 1. So that's also why this is also called a phase gate. X is sometimes called a bit flip gate, and this Z is called the phase gate, because this X flips a bit. 0 goes to 1, 1 goes to 0. But this Z gate keeps 0 as 0, keeps 1 as 1, but essentially just gives the phase with 1. So if I use the operator form for Z, I can write it like this: plus 0. So if I operate 0 from the right, then this 0 into 0, I will get 0 as it is. If I operate 1 from the right, 1 into 1 would be 1, and I'll get minus 1. So this is an operator form for the Z gate. Similarly, another very common single qubit gate is the Hadamard gate, which was also discussed in detail by Aisha in the last workshop. So this Hadamard gate is in matrix form 1 1 minus 1, and what it does, that if you operate it on a 0 state, we can see from here 1 1 1 minus 1 into 1 0. This gives us 1 into 1 plus 1 into 0. So we get 1, and 1 into 1 minus 1 into 1 is 0. So this is 1. And this can be written as 1 over square root 2, 1 0 plus 1 over square root 2, 0 1. And this is the 0 state. This is the 1 state, and this is the 0 state. So I can write it as 1 over square root 2, 0 plus 1. So this is an important gate, because This can convert this state 0 into a state which is a superposition of 0 and 1. This is sometimes also given a special symbol. It's called a plus state. This is essentially just a shorthand for this state. Similarly, we can check that if I operate this header mod on 1, I get 1 over square root 0 minus 1. So this is also a superposition, but now the amplitude of 0 is 1 over square root 2, and amplitude of 1 is minus 1 over square root 2. So when we measure it, the probabilities of getting 0 and 1 is still half and half, but the phase with the 1 qubit state, if this H works on 1, is minus 1, minus. So this Hadamard gate is actually very ubiquitous in quantum computing because this is used to create superpositions. And from this matrix, you can easily see that the operator form of this Hadamard gate would be 1, 1, 0, because this minus is coming with this part, this corresponds to this thing, and then all three are with positive sign. So this is the operator form. Okay, so let's now consider multi-qubit gate. So for that, let me talk about the controlled NOT gate. It's also given a symbol CX. Okay, and before that, let's talk about the multi-particle state. These are called multipartite state. Suppose instead of having one two-level system, let me say this is some two levels of a spin of a particle, and I have now two two-level systems. So here is one, here is another one. So I have two particles. So their states are called bipartite states, and we can define states just like for the single state. And in general, the state is a superposition of their states, but their basis state can be defined like this. For example, let's say this is qubit A, this is qubit B. So when qubit A is in 0 state, tensor qubit B also in 0 state, we can say like 0 sub A tensor 0 sub B. And people also use a shorthand for this. They just write 0, 0, or actually even shorter hand like this, just 0, 0. So the 0, 0 essentially means that qubit A is in 0 state and qubit B is also in 0 state. And sometimes we write like this, sometimes we write like this. When it is understood that the first qubit is 0 and the second qubit, first qubit is A and the second qubit is B. So now this 0, 0 state, we can find its matrix form as well, because this is the tensor of 0 with 0. So 0 state is 1, 0, tensor 1, 0. And the rule for evaluating this tensor product is you multiply this 1 with both of them. So 1 into 1, 1, 1 into 0, 0. Then you multiply the 0 with both of them, 0 into 1, 0, 0 into 0, 0, and you get a 4 by 1 column vector. So this 0, 0 state is represented by 1, 0, 0, 0. Similarly, this 0, 1 state, this can be found by the tensor product of 1, 0 with 0, 1. And we can see that 1 multiplied by 0, 1 is 0, 1. And then 0 multiplied with both of them is 0, 0. So this represents 0, 1. Similarly, 1, 0 is 0, 0, 1, 0. And 1, 1 is 0, 0, 0, 1. So these column vectors specify these bipartite states. And using this, we can also define the general 2-qubit operations as 4 by 4 matrices in general. Okay, let's now talk about the control X gate. So a control X gate has a symbol like this. And let's say we have a qubit A and qubit B in some state A and some state B. So this is defined in a way that this qubit remains as it is, and the second qubit is applied with an X gate. So this is essentially an X gate. So it's applied with an X gate if this A is 1, and it's left alone if this A is 0. But actually, a better symbol, and maybe it's a symbol which is used in some of the books, is like this. So this is an X gate controlled by this qubit. So sometimes this is called control qubit, and this is called target qubit. That depending on the control qubit, you specify what happens to the target qubits. So its truth table can be found like this. So let's say this is input, and let's see what is output. So if input is 0, 0, and imagining that I'm specifying input as control left and target right. So if this control is 0 and target is 0, we get 0, 0, because control is 0, so nothing happens to target. If control is 0 and target is 1, we get 0, 1. If control is 1 and target is 1, and target is let's say 0, so 1, 0 goes to 1, 1. Now you see control is 1, so target is flipped, 0 goes to 1. And if control is 1 and target is 1, then it becomes 1, 0. So the target is flipped if the control is 1. And from this, we can actually prepare its operator form as well for this control X gate. This control X gate is essentially because this 0, 0 state is converting to 0, 0. So 0, 0. So this 0, 0 converts to this, plus 0, 1 goes to 0, 1. So 0, 1 goes to 0, 1, plus 1, 0 goes to 1, 1. 1, 0 goes to 1, 1, plus 1, 1 goes to 1, 0, 1, 1 goes to 1, 0. So we can prepare its, operator form like this. So this is how we work out the applications of these 2 qubit gates. So this is actually a gate which is also sometimes called entangling gate, because we have operations such that the operation on these qubits is related to each other. The state of this qubit is determined by the state of this. So at the end, we get a state which is, the result of both the states of the qubits. But we can sometimes have gates and qubits which are independent from each other. So for example, let's say I have this qubit and I don't do anything to it. I just, it's an identity. And then the second qubit, let's say, has an X operation. So now this is much simpler than the control X gate, because this means that whatever is the state of this qubit, this always goes here. And the state of this qubit is always flipped. So this, we always get XP over here. It's not a control X operation. So the truth table for this would be this. If I have, let's say, A here and B here, so 0, 0, 0, 1, 1, 0, 1, 1. So this A always remains A. And B always flips. So 0 goes to 1, 1 goes to 0. 0 goes to 1, 1 goes to 0. So this is this operation. So this is the output. And I can write this combined unitary operation something like this. So identity tensor X. So identity is operation on this qubit and X is operation on the second qubit, which means that if I write this, identity as 0, 0 plus 1, 1, that's what identity is. It's it has 1 at the diagonal elements, and then this X, we already know this X is 0, 1 plus 1, 0. And now using the tensor product, I can find this, state again. So this 0 into 0 is 1. So I get 0 into 1. This 0 into 1 is 0. So this product goes away. This 1 into 0 goes away. This 1 into 1 will give me 1 into 0. Actually, this is little bit, yeah, this is not an inner product. So we made an error. Let me just do it again. So this is essentially 0, 0, tensor 0, 1. 0, 0, tensor 0, 1. Which means that I combine this left qubit with left, and then there are other terms. And the right right with the right. So this becomes essentially 0, 0, 0, 1. So this term becomes this. Similarly, when this is combined with this one, so this 1 and this 0, this becomes 0, 1, and this 0 and 0 becomes 0, 0, and so on. So this is how we can find the operator form of this, multi-qubit gates. We check if there are any questions in the chat before I proceed. Okay, so the good thing is that there's no question so far. So if there is any question so far, you can type in the chat. Otherwise, let me resume. Okay. Let's now do a Hadamard gate on multi-qubits. So, because this is the key operation on what we are going to do later on. Hadamard on multi-qubits. Suppose I have 2 qubits and I perform Hadamard on one and then the Hadamard on another. So suppose this is initialized to 0 state, this is initialized to 0 state. And let's see what's the output here. So the output state, let me call it some psi, can be written as the tensor product of state, let's call it A, and this state B. So this is just A tensor B. So what is A? A is Hadamard on 0, and this B is also Hadamard on 0. This is sometime actually also written as like this, Hadamard on 0, 0, or maybe just Hadamard. So these are just notations. So like when you see Hadamard tensor 2, it means there are 2 Hadamard acting on 2 qubits independently. When you see 0 tensor 2, it means that these are 2 qubit 0 state. So when you can write it explicitly like this, and this essentially means exactly this thing. So let's get back here. So when Hadamard is applied to 0, I get the plus state. Tensor, when Hadamard is applied to 0, I get the plus state. So I can either write it as plus plus or just leave it as it is if I want to express it in plus minus basis. But let's see, we want to see the state in 0, 1 basis, which is sometimes called computational basis as well. So to find the computational basis state, let me write this plus as state in 0, 1 basis. So 0, 1 tensor 0, 1. So now I can write it as 1 over 2 square root, because when I multiply this and this, I get this. And then 0 tensor 0 is nothing but 0, 0. 0 tensor 1 is nothing but 0, 1. 1 tensor 0 is nothing but 1, 0. And 1 tensor 1 is nothing but 1, 1. So this is how we can write it. Some people would actually write it like this as well. So let's say x naught going from 0 to 1, x1 going from 0 to 1, like x1 tensor x naught, or just like this, 1 over 2 square, sum over x naught from 0 to 1, sum over x1 from 0 to 1, or you can just write it just x1 x naught. So this essentially means that I have two qubit states which are tensoring with each other, and the state of each one of them is either 0 or 1. And we have to sum over all possible combinations. But and you can imagine that if I have 3 qubits, then I will have to write 3 sums and so on. And as we increase the number of qubits, the number of sums keep on increasing. So that's why people have invented a shorthand notation to represent this state. And this is that we use decimal labels. We use label 0 to represent state 0, 0. We use label 1 to represent state 0, 1. We use label 2 to represent state 1, 0, and we use label 3 to represent state 1, 1. Then I can write this state as 1 over 2 square root, sum over x going from 0 to 3, just x, because this is nothing but 2 power square, 0 plus 1 plus 2 plus 3. And this is just the shorthand notation actually for this thing. Okay, so let's now generalize this Hadamard gate on each of the individual qubit to, let's say, some n qubits. Suppose I have 0th qubit, first qubit, all the way to n minus first qubits. So I have total number of n qubits, and I'm applying Hadamard independently on each one of them. And suppose I have initialized each one of them to 0 state. And I want to see what happens over here. This type of construction, by the way, is called the Hadamard transform. So Hadamard transform is nothing but Hadamard gate on each of the individual qubit independently. And let's see what we get from this. So the output state, let's say psi, is now Hadamard on 0 tensor, Hadamard on 0 tensor, all the way to Hadamard on 0. Now before, okay, let's actually do this. So I can also represent it as Hadamard tensor n 0, or just, Hadamard 0, because this 0 is a label for the 0, 0, 0, 0 state. So coming back here, so this is 1 over square root 2, 0 plus 1, tensor 1 over square root 2, 0 plus 1, all the way to the nth qubit. And if we multiply all of them, we will get a state like this: 1 over square root 2, 0, 0, 0 plus 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, and that's how it will continue all the way to 1, 1, 1 state. Since we have n qubits, so this corresponds to decimal 0, this corresponds to decimal 1, this corresponds to decimal 2, this is 3, and then the next state would be 4, and this is just 2 power n minus 1. So it means that I can, and then there is this 2 power n over here, because there's 1 over 2 square root, 1 over 2 square root, all with all n qubits. So this becomes 2 power n square root. So I have 2n power square root, x going from 0 to 2n minus 1, sum over x. Or if I define my capital N to be 2n, then I can write it as 1 over n square root, sum over x from 0 to n minus 1, x, which is nothing but 1 over n square root, 0, 1, 2, 3, 4, all the way to n minus 1 state. And this is actually a very nice thing, because what we did that we started from a state which was 0, and we have, after this n-dimensional Hadamard transform, we have ended up with a state psi, which is an equal superposition of all possible combinations of input qubit states. Okay, because I have +1, +1, +1, so all of them have amplitude 1 over n square root, 1 over n square root, because this is multiplying with all of them. So this is actually the reason this Hadamard transform is used a lot in quantum computing, because it can prepare a state which is an equal superposition of all possible basis states using n qubits. Okay, so before I get to my quantum search algorithm that I have to explain in this workshop, let me just do one thing, and then we will go to that. And that is that what happens that if we have general input state, and what does the Hadamard transform do to it? For example, we discussed what happens if the initial state is initialized to 0, 0, 0, and we saw the output is the equal superposition of all computational basis state with amplitude 1 over n square root. But what if, you know, some of the states are 0, some of the states are 1, or maybe 0, and so on. So all states are different. So what happens then? To do that, let me introduce some symbolism now. And that is that, let me get back to this thing again. So when we apply Hadamard to 0, we know that we get this thing. We get 0 plus 1. And we Hadamard is applied to 1, we get 1 over n, 1 over 2 square root, 0 minus 1. So what if I want to find Hadamard for this general x? So I can see that I can, let's actually use a symbol k for this. So if I want to apply Hadamard on a qubit with the state k, I can write it as 1 over 2 square root sum over x going from 0 to 1 minus 1 power k dot x x. And we can see that when k is 0, that Hadamard is being applied to 0. So this 0 into x, whatever x is, this minus 1 power 0 is plus 1. And when so this is then just a sum of 0 and 1. So we get 0 plus 1. But when k is 1, that this we have the second case, then k is 1. So when x is 0, 1 into 0 is 0. So minus 1 power 0 is 1. So we recover the first qubit when x is 0. And when x is 1, but k is already fixed to 1. So 1 into 1 is 1, and minus 1 power 1 is 1. So this becomes minus. So I recover the second state. So it means I can write the Hadamard on a general qubit state k like this. So using this, we can have a method of finding the Hadamard transform of a general input state. For example, let's now see what happens if I have this Hadamard, n dimensional Hadamard applied to this state, let's say kn minus 1, kn minus 2, all the way to k naught. So this is essentially just Hadamard on kn minus 1, tensor Hadamard on kn minus 2, all the way to tensor Hadamard on k naught. So I can write this as 1 over 2 square root sum over kn minus 1 going from 0 to 1 minus 1 power kn minus 1 multiplied by, sorry, this is, let's introduce the symbol xn minus 1 for this. Then for this one, it would be 1 over 2 square root sum over kn minus 2 going from, not sorry, kn minus 2, x n minus 2 going from 0 to 1 minus 1 power kn minus 2 xn minus 2 xn minus 2, and all the way to the last qubit 1 over 2 square root sum over x naught going from 0 to 1 minus 1 power x naught into k naught sum over x naught. And if I combine all of them, I can write 2 power n sum over let's say x going from 0 to n minus 1 minus 1 power k dot x x, where this k dot x is nothing but a dot product like this. So this k dot x is essentially kn minus 1 xn minus 1 plus kn minus 2 xn minus 2 all the way to k naught x naught. Because when I combine these product terms, so minus 1 raised to power, all these powers would add up and they will become this. And then this state xn minus 1, xn minus 2, x naught, etc. I have given them label x. So now, in general, when I have this H tensor n operating on the state k, I get the Hadamard transform like this. And if this k is 0, we can see that when k is 0, this is 1. So I get the Hadamard transform on the 0 state. Okay, so this concludes the the introduction to different things that we will need to discuss our algorithm that I will discuss now. But let me see if there are any questions in the chat. All right, so the good thing is that there are not any questions in the chat so far. So it either means that most of you are familiar with what we have done so far already, or you're having trouble comprehending this. Okay, so let's come to know what is quantum computing and how it's different from classical computing. And for that, let me briefly discuss, the classical versus quantum computing model. And then I will discuss a particular algorithm, and then we will use the gates that we have studied so far to solve that problem. So classically, we are all used to, this sequence of steps that we do one by one. So we have a certain gate, a certain register, we load some information in terms of bits, and then we keep on processing, and maybe at some points we have some repetition or so on, but we are just modifying this register that we have that contains our bits, and at the end we have some output. So we have like a sort of a sequence of certain steps that are operating this this register of bit that we have. And at one time, this register holds one value one value at a time. For example, if this is an 8-bit register, so I might have 10001 something, and then at another time I might have something other else, and so on. So that's how the classical computing works, at the foundation. Quantum computing, on the other hand, is somewhat similar in some sense, but little bit different in a particular sense. So in quantum computing, we also have, a register, let's say, containing a bunch of qubits. But now their states may not always be just 0, 1, 1, 0, 0, 1, etc. But the crucial difference between this and the classical computing is this, that we could have a superposition of these states. For example, our system could be in a superposition of 0, 0, 0, 0 plus 1, 1, 1, 1 state. While in the classical computing, our register have either, let's say, 0, 0, 0, 0, or it has 1, 1, 1, 1, 1. But our quantum register can have a state which is superposition of these different states. For example, if this is an 8-bit register, there are only 2 power 8 possible values that this register can hold. But crucially, at one time, it can only have one value. But on the other hand, the quantum computer register, if let's say this is an 8 qubit register, this can have a state which are many in number, infinite actually. But more crucially, this can have a state which is superposition of all of these states that the classical register can have at one time. And this, superposition gives us the ability to process faster than on a classical computer, because due to this superposition of states, we can, when we do, let's say, an operation on this register, we are essentially doing operation on all of these states simultaneously. Even though at the end, when we will measure, we will have only one of the state, but during the processing part, we have access to all of the states at one time. So this is how it's different. And also, this means that when we start with a certain number of qubits, at the end of our unitary operations, we still have the same number of qubits, which means that the number of inputs and number of outputs in a quantum computer is always the same. You're not going to destroy any inputs. While in classical computer, logically, we can do that. For example, our AND gate and our NOT gate. So this has one input, one output, but our AND gate has two input and one output. So this essentially is destroying some information because you cannot go back once you have the output of AND gate. But in quantum computer, whatever our quantum computing algorithm is, it always has the same number of input and output so that we can also go back. So this is sort of a reversible computing. Okay, so in general, the quantum algorithms essentially works like this, that we generally prepare a superposition state, which is the superposition of all possibilities, and then we do some processing. And this processing is essentially sort of an interference where we are trying to increase the amplitudes of those states which we want at the output. And then once we have done this processing on our qubits, then at the end we do the measurements and we get results. And since we have gone from a state which is of equal superposition, for example, let's say it's a 2 qubit circuit, which means that I have 2 qubits, so there are only 4 possible states. And let's say 0 state, 1 state, 2 state, and 3 state. So the first part of most of the algorithm is to prepare a superposition of all these 4 possibilities. Because if you have 2 qubits, at the end when we measure, we only have one of these 4 possible states. And suppose in the answer we want this 3 at the answer. Suppose, for example. So then the job of this processing part is to increase the amplitude of this state 3 and decrease the amplitudes of other states. So that when I do a measurement on this one, so since I have a superposition of all these 4 states, but when I do measurement, I have the highest probability of measuring this 3 state at the output than these other 3 states. And then my algorithm would be successful in finding number 3 at the output. You'll see when we do the algorithm actually how this works. But these, and then you have many other algorithms, but almost all of them work on a principle like this, that using quantum algorithm we are working with superposition states, and our goal is to increase the probabilities of those states which we want at the output and decrease the probabilities of those states that we don't want at the output. And that's why thinking about quantum algorithm is actually different than thinking about classical algorithm. Because classical algorithms, they're essentially the type of thinking that you need to work out the classical algorithm is something that we're all trained in from our childhood. Okay, so we instruct somebody to do something. You can always tell them, okay, let's say you want to fetch something from somewhere. You can, okay, take the bus, go there, get that thing, then ride the bus and come back, and then hand it over to me. And the classical algorithm are essentially, they are also, the same. We program a computer in almost the same manner. We say, okay, do this, multiply that, add this, subtract that, and so on. At the end, we have something that we want. But in quantum computers, the thinking about programming is in a quite different way. We are not, if we, let's say, have input state 0, and from 0 we want to go to 3. So it's not essentially, okay, add 0, 1 to 2, 2, add 1, and then add 1, then add 1, and then you get to 3. But essentially we think in these terms, that we have a state which is superposition of these many states. So what do I do to, what sort of gates or circuits I use, so that I can increase the probability of this state and decrease the probability of other states. So that's how the quantum algorithms are actually worked, and that's how quantum computer essentially works. To see this thing in action, let's actually come to this problem, which is the search problem. Rather, let's call it the unstructured search problem. Suppose you have a bunch of data, let's say some names, or let's say some characters, A, B, C, etc., all the way to Z. And you want to, let's say, find the character W. And this database is not, alphabetically ordered, but it's, randomly structured, and so on. So there's no structure to this database. So classically, let's say there are n number of items, n items. So classically, what we will do, we can, let's say, start from one side. We say, okay, let's check the first element, and you check it's Z, it's not W. So you say, okay, let's go to the next one. You go to the next one, you check it's W, yes, it's W, so stop. So you have found W. So if you're lucky, you can find it, in 2 steps. But if your W happens to be the last element, then you will have to go through it, n times before you are able to find the W. So your worst case scenario requires you to do n searches through this database. And if you don't want to start from one side and go all the way to the other side, you can do slightly better. If you say, okay, I will randomly access an element and then check it. You let's say randomly pick 10th element and you check if it is Z. No. You, let's say, then randomly pick 26th element. You check it's W or not, it's no. So then you go and check randomly the 3rd element. And so if you do randomly, then after n by 2 random searches, your probability of finding the element has doubled, because you have already searched half of the space. So even with a random algorithm, you still need operations of the order of n by 2 to find what you're looking for. Same is true, let's say you have a database of names, or database of numbers, and so on. If you don't have any structure, like your data is randomly shuffled, then the number of queries that you need to send out to this database is proportional to the number of elements in the database. If there are 1 trillion elements in this database, you need about 1 trillion searches through this database to find your what you are looking for. So classically, even so far, there's no algorithm which is known to search through it faster than n by 2, unless there's some structure to this database. But that's not something that we are considering. We are starting with an unstructured database. And let's see if we can work out a quantum algorithm that can search through this element a bit faster. Okay, let me see if there are Any questions? All right, so if you have any questions, you can remember always post in the chat, and I will be periodically going through the chat and try to answer those questions. All right, so let me now discuss the algorithm, which is the Grover search algorithm. So Grover algorithm is this, that you start your qubits in 0 states, and suppose you have n qubits such that capital N is equal to 2 power n, that if you have, uh, 8, elements to search for, you take 3 qubits because 2 power 3 is 8. And then you perform a Hadamard transform, which essentially means that you perform Hadamard individually on each qubit. And then you perform a unitary operation, which is usually called the oracle, because this is an operation which have access to your database, and it's able to recognize the solution. That when you index your solution, you give the index of your solution here. For example, if you're looking for 101, which is your solution, and if 101 comes at the input, this is able to recognize the solution. And this is an oracle which is able to recognize the solution, and it's actually able to mark the solution with a minus sign. And then you do the Hadamard transform again, and then you do another unitary operation. We will give it a symbol UF naught, and this is a very simple unitary operation which just gives a minus sign to every input that comes other than the 0 state. And then you apply Hadamard again on each of the output, and you do this part, let's say R number of times, and then you measure your qubits. And our claim is that with high probability at the measurement, you will find this, the number that you're looking for, the index of the data that you're looking for, that this UF has access to. And let's see how. This UF is an oracle which gives you minus sign with the input if your input is equal to the W state that you're looking for. Suppose out of all the elements 0, 1, 2, all the way, W is something that is your solution. So when the input is that W, it multiplies the input with a minus sign. Otherwise, it gives you the input at the output as it is. So which means that this UF can be written in a special way. That this does this, that if the state is W, it gives it a minus sign. And if the state is not W, it gives this, it keeps it as it is. So it means I should write it as when X not equal to W, whatever the X is, I get X at the output. So this is the operator form of this, UF, and I can also write it like this. So suppose these are all zeros, 1, 1, 1, 0, 1, 1, 1. So this means that this matrix, when it multiplies with something, when the element corresponding to W comes, it gives it minus sign and it doesn't do anything to other, it gives 0. And when this matrix multiplies with any state which is not W, it keeps it as it is. And when W comes in, it gives also it multiplies with 0 and annihilate. So if W comes from right side, this gives it minus sign, this does nothing. This this part converts it into 0. So the overall action is that if W comes in, you get a minus sign, and if X comes in, this gives it 1, and this multiplies with 0, so you don't get anything from here. So this is the representation for UF, and I can also actually write it like this, because, or you can also think of like this: 1 1 1 minus 1 1 1 1. So instead of thinking UF like this, you can also think of like this, that it gives 1 to each state as input, it keeps it as it is, but if the state W comes in, it multiplies with minus sign. And I can also write it like this, because this can be written as something like this: twice minus 2 0 0 0 1 0 0 0 plus 1 1 1 1 1, because this element into minus 2 is minus 2 and plus 1 is minus 1. So this is this, but this gives me a nice way of representing, because this is nothing but minus 2 W, and this is nothing but identity. So this is my UF, identity minus 2 WW. Similarly, the UF naught is this thing. So it doesn't do anything to 0 state. So the element corresponding to that is 1, and it gives minus 1 to all other state. Remember, the 0 state, the of n qubit is 1 0 0 0 0 0 0, and similarly the 1 state is 0 1 0 0 0, 2 state is 0 0 1 1 1 0 0 0, and so on. So that's why there's a plus 1, because this UF naught doesn't do anything to the 0 state, and it gives a minus sign to all other states. So I can also write this like this: twice 0 minus identity, because there's a minus 1 for all of them. So if you can check that, this essentially means this: twice 1 0 0 0 0 0 minus 1 1 1 1. So 2 into 1 2 minus 1. So the first state is plus 1. So all other states are minus 1 1 1. So this is a operator form representation for the UF naught. All right, with this, we are now able to analyze our Groover algorithm. And let me just draw the circuit again in the short notational form. So I have this n-dimensional 0 state, and we apply the Hadamard transform. This is the n bit, and then I apply UF, and then I apply the n Hadamard, and then apply UF naught, and then Hadamard, and then measurement. So let's start from this step. So in the step number 1, my state psi is 0. After the first Hadamard, my state psi is something that we have already worked out: 2 power n sum over x 0 to 2 power n minus 1 x, and actually let's just use 1 over n square root sum over x from 0 to n minus 1 x. And actually, let's give it some special name. Let me call it S state instead of psi to distinguish it from the input state. And this S state, let me write it in a certain way. So let's bifurcate into 2 parts, because this is nothing but something like this: 0 1 W and all the way to n minus 1. So this W is something that we are looking for. So let's partition this superposition state S into 2 parts. One part is that contains everything except the W state. And let me separate the W state as from this. Now, what I can do that I can put an n minus 1 here and n here. And then to keep everything like this, let me put n minus 1 here and here. I'm doing this because these are, n minus 1 elements now. I took one out on the other side. So to make it a normalized state, let me call it some W perpendicular. I'm dividing it with n minus 1. So I'm multiplying with n minus 1 over here, plus 1 over n square root W, where this W perpendicular is 1 over n minus 1 square root sum over x from 0 to n minus 1, but x is not W, over x. So this is my superposition state S after the first Hadamard. So I have n minus 1 over n W perpendicular plus 1 over n square root W. And we can also see, since its square and its square is 1, because it's a normalized state, you can check if you take square of this and square of this, this is 1. So let's call this some sine of theta, and this some cos of theta. So then this becomes cos of theta plus sine of theta, where sine of theta is 1 over n square. So this is my S state. All right, just introduce another parameter theta, which is related to capital N, using this for easiness, and also later on to get a insight into what is happening. All right, so let's now go to step number 3. In step number 3, I have to compute the next state. Let's call it some S prime, which is just the UF operated on S. And UF, if you recall, was nothing but I minus 2 W into S. So when this I operates on this S, I get cos theta W perpendicular plus sine theta W. And when this minus 2 W operate on this one, I get 0, because this W and W perpendicular are orthogonal. You can check. So this is 0. So when this minus 2 W operate on this part, I get minus 2 sine theta W into W 1, and I'm left with W, which is nothing but cos theta W perpendicular. This is plus sine theta. This is minus 2 sine theta. This becomes minus sine theta W. So this is my S prime state. All right, now we have this part, which is the n-dimensional Hadamard, UF naught, n-dimensional Hadamard part left. And let's call this something V. So this V is Hadamard 200 minus I. This we just worked out before into Hadamard. So if this Hadamard goes in, this is Hadamard on 0, Hadamard on 0, and there is Hadamard. So this is Hadamard square, and as Aisha was telling you, this is identity. So, and this is Hadamard on 0. We have already worked out that this is S state. So this is S cat, and this is S bra. So this is identity. So this V operator is also called diffusion operator initially, but some people also like to call it reflection operator. Is this 2SS minus I. And let's now operate this V operator and state S prime. So this V operating on S prime will give me 2S S minus I into cos theta omega perpendicular minus sine theta omega. And just recalling that this S state is nothing but cos theta plus sine theta, and this S is cos theta. Sorry, this is plus sine theta. No, I made it. This was okay. So this is W, and this is W, this is W. Okay. And this is operating on this part. Cos theta W perpendicular, sine theta W. And then this is also multiplying with the identity. So I have minus cos theta W perpendicular minus plus sine theta W. Let's see what we get. So we get when this one is inner product with this thing, we get cosine square theta minus sine square theta. And cosine square theta minus sine square theta is here. And for this state, we now get 2 cos theta into cosine square theta minus sine square theta. This becomes 2 cos cube theta minus 2 cos theta sine square theta, and then cos theta comes from here, minus cos theta. For this omega state, we get 2 sine theta into cos square theta minus sine square theta. So this becomes 2 sine theta cos square theta minus 2 sine cube theta. And from here I get plus sine theta. And if I put the expression for sine square theta as 1 minus cos square theta, I get 4 cos cube theta, and minus 2 cos theta minus 3 is minus 3 cos theta omega perpendicular. And over here, when I substitute for cos square theta, we get minus 4 sine cube theta, because minus 2 is minus 4, and then plus 2 and plus 1 is plus 3 sine theta into W. And you can check this identity that this is nothing but cosine 3 theta, and the next one is nothing but sine 3 theta. So this is my Vs prime. Okay, so we are done with the most of the derivation. Let me see if there are any questions. So here in the chat, in quantum computing, the part where amplitude of one output is increased, would that part take up some computational power, and does it place any bound on complexity of problem? Yes. So when we have to increase amplitude of something, we have to do some operation to do that. So it means it requires applications of gates, and of course it's why we have the computational complexity has to take into account of that thing. All right, so we are done with the major part, and let's just see how the overall algorithm now works. Because what has happened is this: that if I think of a plane, let me call it some sigma plane, spanned by vectors omega perpendicular and omega, we saw that our state S, which was the superposition state, was cos theta plus sine theta. So cos theta was along this and sine theta along this. So it means in a plane spanned by omega perpendicular, this is a vector making angle theta with this thing. And our S prime state was cos theta minus sine theta. So it means it is reflected around this axis like this. So let me mention the algorithm here again. UF naught. So what this Hadamard did was prepare this superposition state. This UF essentially flipped it and make the state S prime, which was cos theta minus sine theta. And then this part, which we call V, essentially took it back from here and gave us a state Vs prime, which has angle 3 theta, this cosine 3 theta. So essentially, this is a state like this. So this angle is 2 theta. Now, at the end, we want an output W. So it means that we have been able to take our state S from making angle theta with W perpendicular axis. We have been able to rotate it towards what we want by an angle 2 theta. So if we keep operating this V part and this UF part, so if I, let's say, instead of once, I did it again. Let's say I prepare its copy and put it here. So after another copy, this 3 theta will become 5 theta, this will become 5 theta. And after R repetition of this part, my vector will go from here to here, then here, and ultimately somewhere close towards the 90 to the perpendicular axis. So after R applications of UFV on our S state, we will reach cosine 2R theta plus theta omega perpendicular plus sine 2R theta plus theta omega. So if we select an R such that this angle is 90 degrees, so then this would be close to 0 and this would be close to 1, and our output state would be approximately close to omega, which means that if I take 2R theta plus theta approximately pi by 2, I should be able to rotate my state all the way from this S state to a state close to the perpendicular axis. And let's just compute this R and then I'll get back. So from here, if I take theta, so I want to find R. So let's say 2R theta is pi by 2 minus theta, and R is equal to pi over 4 theta minus half. And if you recall, theta was sine inverse 1 over n square root. So this is, and if I have this n large, then theta is approximately 1 over n square root. So if n is large, then this theta is 1 over n square root. So this becomes pi over 4 n square root minus half. And we see that our R is of the order of n square root. So if my n is a million, then I only need 1,000 repetition, 1,000 R to find the solution. Whereas classically, I needed to access the database about 1,000,000 times if my n is million. So if I had million elements in the database, classically I need to access my database about 1,000,000 times. But quantum mechanically, I can find the state W by accessing only by 1,000,000 square root, which is roughly like 1,000. So by exploiting the superposition and by doing the interference sort of, so this part is essentially doing the what initially I was calling interference, because this is what is increasing the amplitude of the state in this direction. And actually, we can look at this algorithm in a different way as well. Not just, in this geometric picture, but I can also look at this algorithm in this way. That when I did the first Hadamard on my state 0, I prepared this state, which we called S. So this essentially was a state like this. So 0, 1, 2, all the way to W n minus 1 state. All states had equal amplitude, and the amplitude was equal to 1 over n square root, because that's what S came out to be. S was 1 over n square root, sum over x going from 0 to n minus 1. And when we passed it through the oracle, which marks the element. So when it passed through the oracle UF, what UF did was to mark this W state with a minus sign. So it didn't do anything to the other states, but this state got flipped. So this is what UF did. But when it passed through the V operation, which was the Hadamard, UF naught, Hadamard. So when it went through V, we actually came to this state, because our state went from S prime, which was cos theta W perpendicular sine theta. So this S prime was minus. So it went to this state, cos 3 theta plus sine 3 theta. So sine 3 theta is larger than sine theta, and cos 3 theta is smaller than cos theta. So the amplitude of these states reduced, and amplitude of this W state increased. This is what we got after one application of V. And when we repeat the whole process, we made these amplitude even smaller in the next step, and increase the amplitude of this state even further, so that when we do the measurement in the last step, we actually are able to increase this to find this state W with a higher probability than other states. Any questions so far? Let me see the chat. All right, so I have 7 minutes, and in these 7 minutes, I know that it's not possible to understand quantum computing in just 1.5 hours, but I would still like to show you an implementation of this algorithm that you can see actually on the web. And so for that, let me actually share my screen again. All right, so this is a file that I have already prepared, and I'm not going to go into too much detail. You can check the detail yourself. Actually, you can see, you can access one of my course on quantum computing that explains all of these things on this website, quantum.org. So if you go to the courses, you see introductory quantum computing. So over there, you can check all the lectures all the way from the basics to advanced, like Simon algorithm, Fourier transform, phase estimation, and many other algorithms, including this Grover algorithm. And I have also explained how you can, run your algorithm on IBM Quantum Computer, which is provided in cloud for free. And then you have access to, lecture notes and videos, etc., but also the labs. For example, for this Grover algorithm, I have this lab over here. So this will take you to the GitHub, and you can find the code over there if you want to implement. But let me briefly discuss it on the Jupyter notebook that I have done for this. So there was one part that I haven't explained actually, and that is how do you work out the circuit for UF? And that's actually a bit longer thing in itself. And maybe on this website, you can find a couple of lectures on which are dedicated to finding the circuits for these oracles. So general scheme for designing phase oracles, etc., Grover oracle. So you can go over here and see how to design these oracles. But here, for example, I have designed an oracle that that marks two solutions, and then there is this phase oracle for Grover, which does this thing, and then if you implement this circuit, let me just show you. So this is sort of the implementation of this circuit. This UF that you see is the Grover oracle, and this V that you see is the oracle for Hadamard, UF naught, and Hadamard. So this is combined. And you see for this case, there are two solutions that I have marked, not one solution. So because your database can contain more than one solution. So for two solutions, your R comes out to be 2. So I have 2 repetition of this UF and V. So after these 2 repetition, if you run this algorithm, this is just on the simulator. So actually this is for 1. So you see this 1 1 1. This is a solution that was marked in this program. So once you work, when you measure the states, you see the probability of this state to be highest and probability of other states to be lowest. So when we do measure, we find this state with the high probability. All right, so let me stop sharing and pause for any questions that you might have. Let me just copy the website address here if you want to access the lectures on other algorithms, and also the Jupyter notebooks that implements most of these algorithms on IBM's quantum computer. Okay, so if there are no questions, I would like to thank you all for joining this workshop. Okay, so there's a question, is it open for all? Yes, so the course is already done. It was conducted in spring, and you have access to all the materials of the course on one page. So you can watch other algorithms if you are already familiar, but if you need to understand the basics, you can start from the basics and see all the course over there. Okay, so happy conferencing for the rest of the conference, and I would be happy to answer any question over the email as well if you have any. So with this, I would like to thank you and say goodbye. So, and I would give it over to the host